Hi, welcome back to the machine learning course. So in this video, we are talking about the ground truth. In the context of regression, ground truth refers to the actual observed values of target variable used for both training and evaluating. So if we go back to the simple regression that we have and we run this again, so here, based on that definition, this red scatter of dots is our ground truth. These red dots, which they have an X and a Y, is basically what we know about X and Y. And we want to use this to build our model. It's worth noting that the underlying truth, the actual ground truth that we are interested in, is the y equal b plus ax without the noise or without any other parameters added to it. That's the thing that we are interested to discover with our model. But the fact is, in real life, when we are observing, when we are measuring the target value, we don't have a choice to only measure the underlying truth that we are interested. It always comes with some noise or measurements. So therefore, in our modeling, we are considering the whole thing, the underlying truth plus the noise, whatever we can measure as our ground truth. And it's shown as this scatter here. Here you can see that I'm not interested in the noise, but I have no choice. They are part of my ground truth here. And I'm using all these points to come up with this blue model, which in this case can accurately discover the underlying truth from this ground truth that I have. So usually when we are visualizing our ground truth, we kind of discovering what kind of model can fit it. Like here, my ground truth is compatible with a linear model and it's fitted perfectly. But let's consider if our ground truth is something other than linear. Like instead of being a linear function here, we can have a different function. For example, if I have a power of 2 of x here and I regenerate the ground truth, you can see that now I have a curve here and the blue line is not perfectly fit anymore. To see it more clearly, I can change the scope of x. So if x is between 0 to 3, and now we plot the ground truth, which is the red points now, plus the noise, and this is the new line that is fit. You can see that a linear model is not perfectly fit our data here. But for this interval between 0 to 3, you can see that the R square score is not that bad. But we shouldn't be fooled by this number. If we have a power of 2 model instead of a linear one, it can be fit perfectly to this ground truth, and this number gonna be much higher. So this R2 square, we need to be careful, and this is more a relative uh, number for comparison of two scenarios as to rely on the absolute value of the R2 square. So for example here, R2 square for the linear is 93%, but for a polynomial or a quadratic model that we can fit on this data, we're gonna see this is gonna improve uh, when we are building those models. We can also test other functions for our underlying ground truth and see how the linear regression fit that. So instead of this function, we can have a sine function, for example, and if we run this again, so this is our ground truth now, is oscillating based on the x, and our model, a linear model, we can see that it's a very poor fit. Um, and if you can see from the R2 score that the, from the R square score that is also shown that this is not a good fit. So basically from here we can understand that the limitation of the linear regression. So if the ground truth is compatible with a linear function, then the linear regression is appropriate. But as we saw here, if our ground truth is something else, then the linear regression is not appropriate, and then we need to find other regression models that can fit a better model to our data. Then we can improve our uh, evaluation of the model, and we can have a better prediction. So here you can see the importance of model selection based on the ground truth, based on our data set. And here, because our data was generated by us and it's one dimension input, it's a simple regression, and we can visualize the whole data as a scatter, it's easy to see that if a linear regression gonna fit the data or what kind of regression gonna be better. But in reality, when we are dealing with multi-dimension input and visualizing uh, like all these dimensions at the same time is impossible, and the data is more complex than this. It's not very trivial how to choose the model, and we need to slowly build this intuition towards choosing the right model, uh, and then from there we can feed that model and improve the model. But choosing the right model is very important in machine learning topic. And as we saw here, our guide towards choosing the right model is the ground truth. Our data set is guiding us towards choosing the right model. And that's why these methods are called data-driven methods.